Hello, good morning. My name is Díaz-Salamanca. I am a PhD student at the University of Oviedo, and it's my pleasure to be here today with you to share this work entitled Probabilistic Methodology for Fatigue Life Prediction under different specimen size and critical parameter distribution, which has been conducted in cooperation with our colleagues from BREA. This is the main outline of the presentation. I will start with a brief introduction and motivation to the topic. Then I will continue with the experimental campaign we use to validate the methodology we propose in the third step, which is divided also in two small steps. Now, first, I would like to introduce how we can proceed or how we can assess the pure scale effect in fatigue, and also how we can proceed when we have to include the scale effect, but also when we have, for example, a component or a specimen in which the stress distribution or what we call the critical parameter, we can think also about strains, what's on top and other parameters, is not uniform. And finally, I will draw some conclusions of the work. So let's start with the introduction. Yes. Perfect. So as we know, it's the usual approach when we test different specimens in fatigue or specimens subjected to fatigue is to follow the recommendations of the standards with regard to both the geometry and also the law. Moreover, we also know that we have different techniques. Also, in the recent years, there have been some new proposals, or there has been proposed some new tests for testing components. Here we can see some of these examples, such as the conventional uniaxial test, the 3-point bending test, or rotating bending test. So the thing is that taking all these points into account, I think that several questions may arise in our head. For instance, for example, regarding the fatigue life predictions, because although if we follow this different approach, or if we test the same materials following different or using different kind of tests, although using the same, for example, maximum stress value, the expected the fatigue life that we are going to observe experimentally is going to differ, since maybe the region subjected to the maximum stress value, for example, is different. Furthermore, if these observations at the laboratory scale differ, the question is how we can use, how and in what way we can use that information to predict the fatigue life of components, real components in service operation, in service, for example. No? So our goal, or the goal of this work, is try to answer a little bit these questions. The main objective is to propose a methodology to first join evaluate fatigue results from different experimental campaigns, and then to translate this information from the lab to real components subjected to fatigue loads. So I will now move to the experimental campaign, which motivates in part which motivates in part the work, and we also use this to validate the methodology. So in this case, we focus on the S460 NL steel, and several tests were carried out in this material. For example, some microstructure analysis in which we can see the typical microstructure of this kind of steel. Also, some monotonic tests were carried out to obtain the stress and strain relationship for this kind of steel. And we also performed that more than 4 different fatigue campaigns on these steels with the geometry that we can see here in the slide. We use, for example, flat specimens, round specimens, and 3-point bending test specimens and 4-point bending test specimens. And in the following, we are only going to focus in this in the fatigue experimental campaign. It's also important to point out that all the tests that we consider with this methodology were tested under the same stress ratio. The run-out criterion was set to 10 million cycles, and we only consider those specimens in which a crack appears in the surface, in order to avoid any errors and to introduce outliers and this kind of problems that Okay, so now I will briefly show you some of the results we obtained for the different configurations. Here we can see the uniaxial flat specimens. We test 17 specimens with only one run out. You can see also a representation of the results, not the SM field, but the results. Here I show you the test we performed in the round specimens, and I compare, or I put in the same graph that I showed you previously, these results to see what is something a little bit, I think, quite curious, because what we see is that in this case, or if we compare the results from the round specimens with the flat specimens, we can see that small variations in the stress leads to high dispersion in cycles. And this is, I think, very interesting. If we now move to the 3-point bending test, we can see we test 11 specimens, and we obtain the results that we can see here in the slide. Also very interesting, I think, is to see that in this experimental campaign, we obtained 4 run-outs, which, as you may know, is quite costly for us because it's, I would say, a problem. If we continue now with the 4-point bending test, we also obtain 3 run-outs. You can see there the representation. And before moving to the methodology part, I would like to discuss a little bit with you these results because what we can see here is that small, as I previously commented, small changes in the maximum stress for the round specimens leads to big changes in the fatigue life. If we also, we can also see this a similar tendency when we test this material and the 3-point bending test and the, let's say, 3-point bending configuration. And the same is for the 4-point bending configuration. As I comment, the implications of the both points are that it's quite easy to obtain runouts with these configurations with all that this entails. And in contrast, for example, what we can observe is that for the rectangular specimens, we do not face this problem. Maybe it's interesting to point out that the area subjected to the maximum stress is bigger in the flat specimens. So that's interesting, I will say. Now let's move to the methodology we propose to assess this problem. And I divided this part of the presentation in 3 points. Okay, first I will briefly introduce the fatigue model we are going to use to assess this problem, and it's the model proposed by Castillo and Canteli. This model is based on the compatibility condition we established in the SM field between the distribution function of delta sigma. We can think in other parameters I already commented on, in delta epsilon, as we watch on top. But the idea is that we establish this compatibility condition between the distribution function, for example, of delta sigma in this case, for a given number of cycles, and also between the distribution function of the fatigue life, the cycles, for a given stress or delta sigma. The thing is that these compatibility conditions leads to a functional equation. But if we assume that these distributions are variable distributions, we can solve the equation and obtain the analytical formulation of the model that I show you in the slide. Moreover, by applying the weakest link principle, which states that the probability of failure of a component composed by n elements is equal to the product of the local probability of failures of each of these n elements, we can introduce the weakest link principle in the model. And we can see here the term. Here, for the sake of simplicity, I would say I put L, but we can think about we can introduce the weakest link principle or the scale effect in this case, thinking of length, area, volume. It depends on the failure mechanism that we face in our problem. Now that we have seen the basic formulation of the fatigue model that we are going to use, I'm going to divide the proposal in 2 steps. First, we are going to see how we can assess the pure scale effect in fatigue. What is the pure scale effect in fatigue? I put here these 2 specimens. Okay, so the idea is that using the weakest link principle, we can go from for example, the SM field obtained for the specimens we can see in the left side of the slide to the other specimens. Because in these cases, we can directly introduce the scale effect as the unique change we made between the specimens or the different specimens is on the side. but we have to take into account that both sides are uniformly, let's say, subjected to the critical parameter, to the stresses, for example. So in this case, this is the flowchart, or this is the flowchart of the methodology that we propose, and what I want to illustrate in the next slide. So the first thing that we can do is, once we have, for example, in our case, the flat specimens, for example, which are going to be the A1 test, we can derive what we call the primary SM field. The primary SM field is the result of the evaluation of this, for example, experimental campaign referred to a reference scale value, no? Reference area, reference length, reference volume. With that information, we are going to try to predict the results of the other experimental campaign. In this case, it should be quite easy because, as I previously commented, we only have the implementation of the scale effect should be, or mathematically, it's quite easy to implement it. And we are going to see if these cross predictions work well. And we are also going to joint evaluate both the results of both experimental campaigns. This means that we are going to estimate the model parameters, the 5 model parameters, with both experimental campaigns and evaluate the stability of this solution. So let's start, for example, these are the A0 specimens, these are the round specimens, and I select the area as we are going to introduce the scale effect by means of the area. In this case, it's the value that you can see here. And I show you also the experimental results that we already showed. Here we can see the specimens from what I call the A1 specimens, which are in this case, the flat specimens, in which the area is, as you can see, bigger in comparison with the round specimens. And you can also see the distribution of the experimental test in the distribution of the experimental test. Now we are going to use the probabilistic model to derive the primary SM field for both cases. You can now see that there is a difference, in both SM fields, and it's quite interesting because in the previous one, for the round specimens, as we already commented, the problem we face is that we have, let's say, a big dispersion in cycles for a small variation in stresses, which leads to a deformation in the percentile curves on the SM field, as you can see that. Now, what we are going to try is to predict, for example, the rectangular. We are going to predict the SM field of the rectangular specimens based on the SM field of the circular ones. And what you can see here is that it's not with this primary SM field that we have selected, although mathematically the procedure is correct, it's not possible to obtain a good correlation between the experimental results and the model. Let's see what we can obtain, or what we obtain when we move from the rectangular specimen to the circular one. In this case, we do not see that deformation in the percentile curves. And when we introduce the scale effect, we see that more or less the model is, maybe we can discuss some of the results that are a little bit out of the percentile curve. But we see that we are able the model is able to capture the experimental results. What I propose here is to do a joint evaluation of the results. As we can introduce easily the scale effect in the model, we can derive the 5 parameters of the model using the experimental data from both the experimental campaigns, and then try to predict another case, or try to predict the SM field for each of the experimental campaigns. Here I show you the prediction after do the joint evaluation for the circular specimens, and you can see the model is in agreement with the results, but the same happens, for example, when we move to the rectangular specimen. Now we are going to increase, let's say, the difficulty of the problem, because the case I show you was quite easy, but in reality, what we face is that we have some specimens that we test at laboratory scale, but we want to predict now the fatigue failure, or we want to predict the SM field, for example, for a component in which the stress distribution is quite complex. So in this case, we can also apply the weakest link principle, but we have to think about the weakest link principle in another way, because we have to compute the local probability of failure for each of the elements, for example, of the real component. We have to divide the component in small elements in which we assume that the distribution of the critical parameter, stresses, strains, is uniform. and we can compute in that element the probability of failure and then compute the global probability of failure using the weakest link principle. In this case, I propose this, or we propose this this methodology. Okay, we have the primary SN field. I put there the SN field resulting from the joint evaluation, but as we already see, we can use any, let's say, primary SN field. And with that primary SN field, we can derive, using the equation I showed you in the slide, the predicted SN field for a real component or for a more complex case. Then we propose to do some, in this case, we're going to show you some tests for validation and compare the predictions with the validation. And compare the predictions with experimental results, sorry. So in this case, I am going to use the primary SN field resulting from the joint evaluation, but as I show you here, we can use, for example, other type of we can just use, for example, a primary SN field for a unique specimen type. In this case, I show you the SN field we obtained for the flat specimen. With that information, the first thing that we need when we want to translate that information from the lab to a real component to a more complex component is to obtain the distribution of the stresses, for example, or the strains in that component. I put here ANSYS and analytical description because, for example, for the case we're going to face here is a 3-point bending test. We can use it with, we can analytically solve the problem, or we can do it, for example, with finite element, or we can generalize the approach using, for example, some kind of finite element software. No? So once this is, for example, the results for the 3-point, the results of the principal stresses map for the 3-point bending test. Then we have to apply the weakest link principle for each of the elements, and then we can derive the percentile curves for that case. We can do the same here. I show you the same approach. Sorry, because there was a problem with that box. For the 4-point bending test, the methodology is always the same, and I put here the finite element model because I think it's quite more illustrative to show because that's the most general approach that we can use. We can now, I'm going to show you now the experimental results that we have already introduced for the 3-point bending test and for the 4-point bending test. And now let's see the comparison between the experimental results and the predicted SN field, where we can see that the results and the predictions are more or less in agreement. Although I would like to say that maybe it's important in this case, we have assumed a linear model, and maybe we have to take into account some plasticity and for example, in the finite element simulations and so on. And I would like to finish with some of the conclusions, or resuming all the things that we have seen during the presentation. So in this study, we have analyzed the scale effect for different specimen configurations of S400 steel using the Castillo-Canteli probabilistic model. Two approaches has been proposed, one to analyze the pure scale effect and the other one to analyze the scale effect when the critical parameter is not uniformly distributed in the specimen. The methodology that's applied has been validated for the case I have shown you. And as Peter worked, I think that one thing that we can propose is to propose a methodology to derive the primary SN field from, for example, a real component. And I think that could be quite interesting. And also some other points in which we are currently working, and I think that are quite promising, is, for example, the use of Bayesian Markov chain Monte Carlo methods to derive what we call the percentiles of the percentile, but which is the confidence interval of the percentile curves, which can help us during for example, the design stage of critical components. That's all from my side.